Good day, everyone. Thank you for joining this webinar presentation. My name is Philip Payne. I am the technical lead for the Cybersecurity and Information Systems Information Analysis Center, known as CSIAC, one of three IAC domains under the DoD Information Analysis Centers. We operate under DTIC, the Defense Technical Information Center, which is within the Office of the Undersecretary of Defense for Research and Engineering. This is part of our informative webinar series, which highlights current and emerging research and technology developments. Our webinars present an opportunity for accelerating the DoD's leverage of these advancements by primarily increasing awareness and fostering technical collaboration. As such, our organization supports those working in cybersecurity and information systems domain of DoD research and engineering. We do this by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on some of their technical projects. At CSIAC, we provide research and analysis services to help unlock access to information, knowledge, and best practices from the government, industry, as well as academia to stimulate innovation, foster collaboration, and eliminate redundancy. Today, we hope that you enjoy this webinar, and we hope that it serves as a catalyst for community collaboration and improved DoD cybersecurity. Before we get started today, I just want to note a couple administrative items. First, if you are dialed in by phone and would like a copy of the slides, these slides are posted to the CSIAC webinar announcement. You can go to csiac.org/webinars, and you can find today's webinar. When you click on it, at the bottom of the announcement, it will say to view webinar PDF, click here. Second, all participants are muted, but feel free to use the chat using the attendee chat button on the left-hand side of the webinar screen. You can use that to chat with each other. As the moderator, I'll be monitoring the chat as well. However, if you would like to pose a question for the presenter today, which we will address at the Q&A session at the end, please use the audience questions tool, which is at the top center of your screen. It is the icon that looks like a chat bubble next to the file folder. At the end of the presentation today, I will go over the Q&A. For the benefit of those on the phone, I'll read the question out loud to the presenter. If you have any technical issues during the presentation, please have no fear. The full presentation will be available online. Check back to the CSIAC website. The webinar is posted. Once the webinar is posted, the Go To Webinar button will then take you to the YouTube link. It will also be on MilTube as well within a couple days. With that said, I will pass it over to Dr. Deaton. Thank you.
All right. Hey, thanks a lot, Phil. Just a couple wanted to start off before I talk about myself and the content. Just wanted to put out a few thanks. First to DTIC and CSIAC for funding the work that went into putting together this report. This was something that I had been done as part of my regular work, and just to have an opportunity to be able to share it with everyone was just was really, really exciting for me to do that. Also, for those of you who are coming to hear and listen to me talk today, I really appreciate your time and your attention today. So thank you for coming. Also have some other individual contributors, Phil, also, yeah, as announced, I've had some contributions into the document, as well as Ryan Fowler from who worked for contract with CSIAC. Also, a couple of friends I want to thank for conversations and whatnot, specifically AJ Vigil, who gave me some feedback on some of the initial sections and also helped engage me in conversations that were elicited a lot of different ideas that went into this presentation. I have another friend named Bill Hilburn who actually did the same. He actually gave me some inspiration for some of my figures as well. I had another friend named Mahmoud Haroun who also gave me the opportunity to have conversations with regards to how operators are going to move forward in the future with the digital transformation in SATCOM. If there's anybody else who there's also a couple of people from work. Scott Gross and Brian Beaucamp will also let me do a couple dry runs on them, which was really great for me to get some feedback from them on if what I was saying was actually true or not, and let them argue with me a little bit. So that was really, really excellent. So thank you for everybody who helped pull this together. It's a real pleasure interacting with you, and I hope you enjoy this. Just tell you a little bit about myself. You can go ahead and read my bio there, but just to give you something a little bit interesting about myself. is that both my kids when they were younger started wrestling. I was a wrestling coach for about 6 years. I never wrestled before, and I did that. And one of my kids is going to state this weekend, so I'm pretty excited about that. That gives me a little bit of just gives you a little bit more background about me. I like to think of myself as a lifelong learner, so I've worked on a variety of all different kinds of things throughout my entire career. But most of it's all been in telecom, starting in CDMA and then moving in CDMA technology for cellular networks, and then moving into SATCOM. So that's just a little bit about me. So the purpose of this brief is just to explain and explore the topics that are involved in the digital transformation of SATCOM, and just at a very high level, what this digital transformation is the evolution of SATCOM to these next generation architectures, which is going to enable additional capabilities and also allow networks to operate with a higher efficiency and higher performance. And we'll talk about what all those individual components that enable that transformation in evolution. So in my presentation, I've got 4 main sections. The first section we'll just talk about introduction, where we'll introduce some basic concepts and talk about what are the general components of the digital transformation. And then we'll talk about digitization and virtualization of SATCOM networks. And those are probably the 2 most significant components of the digital transformation. And then we'll end it with just a couple of use cases to explore, what types of functionalities are enabled through the digitization and virtualization, which is what comprises the digital transformation of SATCOM. So, and as we get through individual sections, I'll stop to ask if there's any questions with regards to that section. We'll just continue on. So, like I said, the digital transformation, the biggest thing about this is this digital transformation is the next generation evolution of SATCOM. And so what I wanted to try to emphasize here before I actually drive into the introduction is that we're really looking at the precipice of seeing major architectural changes in the way SATCOM ground systems are managed and run, and also most likely seeing current market ecosystems more or less turned inside out. And I think you'll start to see why those things will happen as we go through each individual component of the digital transformation. So what's kind of the motivation between this whole presentation and also the digital transformation? Well, the first thing is that there is a rapidly changing space layer. As many of you know, have read the news, SpaceX is releasing or putting up satellites for their Starlink constellation. Amazon's beginning for their Kuiper Telesat has plans for also a constellation. OneWeb has a LEO constellation now. So it almost seems like everybody and their brothers now jumped on this new, I'm gonna call it bandwagon, but there's a lot of emphasis on LEO technologies right now. However, that's just part of the story. There's a lot of new medium Earth orbit satellites that have been deployed, as well as additional announcements from SES to say they're going to do LEO as well, and also a new plans for launching new GEOs. So it's not just the LEO market, although they're the major part of that story, but there's a lot of different opportunities in space now that are as enabling different ways to access communications and other different types of applications. The other thing too is that the demand for SATCOM has had about a 21% CAGR growth over the last 3 or 4 years. So I mean, if you had stocks that are making that amount of interest, I think you'd be really happy with that. But it's like a really significant amount of demand, and because of that demand and more or less the evolution of that demand, what we saw is a report from the Space Force, which came out in 2020, which discussed the different issues with migrating those systems because of that large demand. But however, there's a huge problem with dealing with stovepipe and isolated systems. And some of these, we'll talk about some of the issues of these are. But let me just put up this figure on this next slide here, just to kind of illustrate what this point is. So in the next 10 years, we're expecting to have about 50,000 active satellites in orbit. That's actually that's like an order of magnitude more than what's up there today. And for the DoD perspective, there's quite a bit of variegation in terms of access techniques and technologies to get to satellite. So like to thank my other contributor, my friend Mike Dean, who also, if you listen to him, he's the DoD SATCOM chief for the DoD CIO. He likes to say, or if you've seen him talk, you'll hear him say that there's 17,000 DoD terminals that are managed and 135 different types of those terminals. The reason for that is that just the amount of variegation that happens across the entire, I guess, the US space ecosystem. So if you look at the individual columns here, you'll see that we've broken things out in narrowband, wideband, protected, and commercial. And these are more or less kind of like waveform categories. But within those different waveform categories, we might have different individual waveforms that are supported by different modems. And then with each individual modem, we might have different models that exist in the ground segments. And then also in the terminal segment, you might have one that's for mobile, within a vehicular. There might be a man-pack type version or sea and air. So because of this level of variegation, there has been a huge push for trying to get things to be common and also um, help try to get things coalesced to something a little bit more interoperable, so that we don't have stovepipe systems. One of the things that too I want also notice to say about this is that at the time of most of these things were development, space was kind of like an exquisite, um, or space or SATCOM was just a kind of like an exquisite area or a market, in that there was very few vendors who would build to these systems, and there weren't a lot of standards and whatnot around these things. So some of those market pressures kind of force things into these stovepipe systems, but also the fact that development, in terms of how SATCOM modems were developed, in particular the conjoining of firmware, software, and hardware together, created this environment or market where we had a lot of different purpose-built boxes or purpose-built appliances for different functions. And so a lot of that kind of drove us into these stovepipe business models. So given that background, and after review of the problem, the DoD has actually released a myriad of RFPs and RFIs to try to address a lot of these different problems. Um, some of them have looking at SATCOM as a service business model, the virtualization of SATCOM satellite modems and waveforms, specifications for next generation architectures, and also next generation tactical terminals. If you look at all four different service branches, you can see quite a bit of effort occurring in all those. And after review of a lot of those RFIs and requests and RFPs and requests for white papers, what I've tried to do is boil down what the key demands of these networks are, in particular the DoD, although there is a lot of application for this into the commercial markets as well. So I'd like to just spend a bit of time going through these key demands, because these are things that are kind of the centerpiece of the SOAR report, and things that I would like to go back to and discuss for issues when we talk about the different components of the digital transformation. So the first thing is freedom from vendor lock-in, and I spoke to this just a little bit earlier on how vendor lock-in happen. And essentially, what happens is when you have highly specialized piece of hardware and firmware and software that go into that, those things are tightly conjoined into the box, which can only be migrated by ripping that out and replacing it with another box. So that problem has contributed to the stovepipe system that we see today, but also the unfortunate can be there are some advantages to do that, but unfortunately, there's some inconveniences that come with that, what those inconveniences are is that we have a market with very few vendors who can operate in that market, in that space, so that DoD's options for obtaining new technology or technology progression is severely limited. The second key demand is just reduction in total cost of ownership. And so for commercial markets, this is much more important, in that their networks need to be able to make money for them to be able to stay in business. So that's very, very important. But however, the DoD costs are also important as well. So any opportunity they can to be able to reduce their operational or capital costs is a win for them, also a win for the taxpayer. The third key demand is ground segment sustainability. And what this means essentially is that your network is able to uh, achieve an effective migration path. There's nothing that'll blocking it. Either they could be operational constraints, they could be logistical constraints, things that just stop you from continuing on to advance your technology to the next evolution. Fourth key demand is terminal and modem agility. And what this means is that and this is something that I won't necessarily cover today, but there's a brief section of the report which talks about the antennas. And there's a great demand within the DoD to have multiple waveform, multiple bands, multiple orbits, terminal systems that can be able to access a variety of constellations and orbital regimes, if you will. And then, like I said, I briefly mentioned waveforms, but modems should be able to operate on a variety of different waveforms. So there might be specific satellite systems, but that might require specific access technologies or waveforms, or some of them may be open to whatever as well. So the flexibility for those to support different types of missions and different types of SATCOM networks is something that needs to be addressed. The fifth key demand is system agility or resiliency, and basically this is the ability for a SATCOM system, or when I say system, I mean including the ground segment and terminal segments. Basically, they're automated, and we can be able to deploy configurations and also modify those configurations based on changing network demand. The final key demand is high computational density and efficiency. And essentially, this is an ever-growing, ever-persistent requirement from the DoD. We just want to do more with less space. And so to be able to increase the amount of computation you can do in a smaller amount of space, it always has great attributes and for the DoD, and also with commercial SATCOM networks, especially those ground segments or gateways that are running out of rack space for putting modems and other equipment into them. And there is one final key demand that I wish I had a little bit more time to focus on, but that is just um, enterprise management systems. And what that basically is just now we have all this SATCOM equipment out. What's the best way to manage not just single gateway or single set of terminals, but let's say you have 5 or 6 gateways and many hundreds and thousands of terminals out there. What's the best way for you to manage that? So that's something I don't cover in the SOAR report, but I do feel like it's something I should mention, that that is still another key demand of the DoD that I've seen. So let's just talk real briefly about the components of the digital transformation, and I'll come back to this figure throughout the entire presentation. And what this shows is basically the dependencies of the digital transformation. And if you're within the box, that means your dependency. So for example, for digitization, for that digitization block to be completed or to be fulfilled, that its dependencies are a digital IF modem, a digital IF protocol, and edge device, and then so on and so forth. So for virtualization to be complete, everything in digitization has to be complete, as well as the other things inside its box as well. And what I'm illustrating here is just kind of like the dependencies of the evolutionary process, but also just to give you an outline of how everything kind of plays together. And we'll talk in this introduction section basically we're going to touch on digitization and virtualization, and then we'll move on to our new to sections where we'll dive in a little bit deeper for what those things are. Okay, let's talk about digitization first. So what digitization refers to is just a lot of people talk about it in if we talk about a normal terminal architecture, we're looking at a SATCOM modem. We hear it like in the middle of the diagram here. The purpose of the modem is to take data bits and transmute those data bits transmute the signals between IP data bits and an analog L-band IF waveform. That analog L-band waveform is then mixed and amplified up to whatever frequency it needs to go, so that it's appropriate to access the satellite network that it's going to go to. When we talk, like I said, when we talk about digitization, or more specifically digital IF interface, what this is we're adding this new interface, which is kind of bust the modem into half. So modem functionality is broken up into 2 major components. The baseband modem on the left there, on the top figure you see there, its job is to take the signals and transmute those signals between IP data bits and a digitized waveform. And then our front end is to take that digitized waveform and then transmute that into an analog signal in both directions. So if we can take this modem and we bust it in half, and we add a digitized interface which takes those digital samples and puts them in packets, and we can send them over an IP network, then we've enabled quite a bit of flexibility into our networks. And this interface that creates this that supports the transport of these digital samples is what we call digital F, and I'll have a lot more to talk about this later on. But essentially, move to this architecture has a many advantages, and the first advantage is that we are separating out what my friend H.A. Vigil likes to call the brains and bronze. So the brains is the stuff, the waveform processing, and all the other things that are very complicated in terms of algorithmic work goes in the stuff on the left. And the edge device kind of becomes the bronze. So basically, all the edge device does is just takes those digital samples and turns them into analog signals. You might even hear people refer to these edge devices as just merely as digitizers. And what the key point to get from this is that we've taken specialized RF front-end hardware and we've removed it from our modem and separated it into its own device. And what that enables us to do is that we've separated any specialized RF circuitry such that we can now move digital IF modem equipment onto common hardware. That's actually a really key point. The other thing too that's very important is that all the specialized brains operations or waveform IP is now separated into its own to a common hardware device, as you see on the bottom here on the left for the digital IF modem. The edge device necessarily doesn't have any specialized IP. It's more or less, like I said, just the bronze. So the fact that we've kind of moved to this architecture, it's going to greatly precipitate the move towards more commodity type architectures, which is really great for people running SATCOM networks. One thing I want to mention too, with regards back to the previous key demands. So as you can see, since we're removing conjoined hardware and software and firmware, and we'll show it even more how it even gets further removed, is that we're making steps towards um, preventing vendors from doing lock-in. And remember when I said earlier that the key how vendor lock-in happens is we have conjoined hardware, firmware, and software. Well, this is one of the good steps that removes it because we're removing this specialized hardware such that we can move to common hardware platforms. And then virtualization gets us that next step out. We'll when we dive down more into digitization and talk about how it affects ground systems, then we'll get to see a lot more of the benefits we can realize from this. But this is really an huge evolutionary step, and the first evolutionary step that SATCOM networks will take. Now we've moved digital IF modem to a common hardware platform. We can start invoking virtualization, and essentially what virtualization is it's just more or less as we are abstracting the computational resources from the hardware to create what's called a virtual computing environment. So with virtualization, we can have multiple independent virtual computing systems operating on the same set of computers or same computers. And what this allows us to do is essentially create a line between what our applications are and what our hardwares are. So this is very similar to installing applications on your smartphone. And that allows us to have a lot more portability in terms of a lot of portability and flexibility in terms of applications. And this is actually something that the mobile network operators have started to do within their own networks. And when we get to the virtualization side, I'll talk a lot more about what those things are with regards to the architectures that they're deploying. But both of it, and the same thing is true for digitization as well. Okay, let's move on. Okay, so I'd like to stop right here and ask if there's any questions on just those introductions. And if you have any questions, go ahead and feel free to type them in the chat box.
Juan, we did receive one question so far.
Okay.
Before we get into that, Juan did hint at the state of the art report. For those of you who are not familiar, CSIAC publishes two SOARs or state of the art reports per year. The SOARs are publications that provide an in-depth analysis of current technologies, research, and the latest technical information available related to one of our technical focus areas. So Juan is actually the author of our latest state-of-the-art report on the digitization of SATCOM networks, which should be published to our website soon. So after this presentation, if you want to have a deep dive into this particular topic, then feel free to read the SOAR once that is published. With that said, I will go over these couple of quick questions now before we continue with the rest of the presentation. So we have one question from Stephen Johnson. He says, what is the maximum distance between the digital IF modem to the edge device?
Oh, that's a really great question. Let's we'll talk about that later on. That's a good segue. I like that. Yeah, we'll address that in this next section here.
Okay.
I think there's another question in the attendee chat.
Correct. So from James Sawal, who builds or owns edge device, and how do we ensure that it is not proprietary?
Oh, that's a you know what? We're going to talk about that too. So these are great questions. I'm glad you guys are chomping at the bit. This is awesome. Yeah, we'll address a lot of those types of things later on. Right? Yeah, that's good. I love it. Yeah. So
Okay.
yeah, this is good. You guys are asking all the right questions, so this is great. And like I said, we'll answer those questions. If we don't answer those questions as we get through this material, please ask it again. So I just wanted to point out that there was a article put out by Major General Lawrence Stridstream. I hope I said that right. In December, he was talking about the transformation of digital transformation of SATCOM networks, and when he said the first step to this dynamic ground architecture is replacing existing analog intermediate frequency IF interfaces with an open digital interoperable standard. And we'll talk about this. Has to go back. This has to do with proprietary boxes and whatnot. How we're going to avoid some of that. So let's move on. Okay. So digitization of SATCOM networks. I'm going back to this figure again just to show you. We're going to talk about digital IF modems, digital IF protocols, and edge devices, and what all those things are and what's involved in terms of how they impact the ground segment specifically. There's going back to our digitized architecture. So we want to I'm just revisiting this back so we can remind ourselves. We got a digital IF modem, which this transmutes signals between IP data bits and digital IF output. And we have an edge device that takes that digital IF, and those signals takes signals from digital IF and transmutes them to analog signals. So that's weird. So if we take this and look at a traditional ground network, what we have is ground networks kind of have three major components, if you will, other than the input for their external data networks. But they have the first component they have is what I call the proprietary modem bank, and that's all the things on the left right there. And this is comprised of many different types of possibly comprised of many different types of modem models. And the outputs of those modem banks are these L-band IF, or outputs and inputs. These are two-way signals. L-band IF. The other major component of this is an L-band switching system. So that includes things like a switch matrix and a combiner and splitter. But basically what this is just the analog equivalent of an IP data switch network that takes signals from the proprietary modem bank, combines them onto a single carrier that's then transmitted out to specific SATCOM network or SATCOM, or just a specific satellite. And that RF transmission system is that last step. So one of the things, and it's typical in these architectures, is that the proprietary modem bank, or just the modem bank and the L-band switching system, is traditionally kept in this building called the Equipment and Electronics building, and the distance that we can travel without the use of specialized equipment is usually maxed out at about 1,000 feet between this electronics building and whatever shelter these RF transmission systems are. So that's one of the limitations. Some of the notes here. Let me look really quick to make sure I'm covering everything. Oh, the other thing too is that as this length, this L-band path increases, there's additional distortion and signal loss that occurs. Some of that can be compensated through some specialized techniques with the equipment. However, there is still a bit of complications that are introduced due to that. In particular, this limited distance about 1,000 feet. But like I said, if you have some specialized technology, you can be able to get that distance up. But traditionally, that's how it works. The other thing too that it's kind of limiting by these L-band switching systems is that they tend to be monolithic in that once I run out of capacity, it can be very difficult for me to add additional capacity without ripping out the entire switch and going to a larger one. And that has direct effects in terms of interoperability. So so that's just to give a little background what the ground segment gateway is. So now that let's say we're going to take this digitized architecture and apply it to the ground segment, what can we expect it to look like? So let's go to that. So in the digitized ground segment, it looks very similar to our previous slide, except we're replacing the proprietary modem bank with the digital IF modem bank, and our L-band switching system is now replaced with the digital IF LAN, and our edge devices then become part of our RF transmission systems. And so the distances we can support with these with single mode fiber and 100 gigabit Ethernet are between 2 to 40 kilometers, and this is just a standard transceiver you can buy off the shelf. No specialized equipment required. And to me, when I saw this, I was actually very, very impressed with the progression that that traditional IP-based switching equipment has been able to get to. So that was actually pretty eye-opening to me. The other thing too is that with an appropriate protocol, the digital IF could hypothetically go to an unlimited distance. If you're going out a wide area network and have a remote site, your digital IF modem bank can now reach sites that are not located in the same, in that same 40 kilometers or not within your own local area network. This is perhaps one of the biggest advantages in terms of resilience, in that we're not necessarily limited now to our individual gateway sites for where our SATCOM traffic can originate from and can go out to. So that's very, very critical. Let me just check my notes here for a few things I wanted to cover. Oh, and like I talked about earlier, the L-band switching system contributing to the length of the analog path, which creates distortion and also signal loss. But now we have a digital IF LAN, which is sending basically data packets through, so there's no loss in terms of signal quality as it travels through these LAN networks. The only path of analog signal we have is very, very narrow and short compared to our previous architecture. There's no need for these analog switching systems, and also the analog-based the digitized or the digital IF LANs can now be increased modularly. So if there's a need to increase capacity, all that's needed is just to buy another switch and connect it up to the network. The other thing too that's really important to this is that with removal of the proprietary modem bank, we're actually reducing the number, because we can't move to common hardware because of this architecture. We're reducing the number of proprietary-based systems or purpose-built modems and moving to some of the common hardware. So this, as you can see, will reduce a lot of logistical complications for managing parts and whatnot, and also enable network operators, SATCOM network operators, to be able to select whatever equipment they want in terms of common equipment, and drive their applications vendors to, like waveform vendors, to develop for that equipment. The other thing too that's it's interesting to point out is that because the edge devices have very little intellectual property within inside them, there's a very low barrier to entry to make these devices. So assuming that we have an interoperable interface for the digital IF, that is actually going to enable these devices to more or less be drop-in replacements. So the fact that we have different vendors developing these devices, or have maybe some proprietary basedness inside them, that necessarily won't impact the performance of these individual devices or the replaceability of them. And the fact that these edge devices, with the proper digital IF protocol, they could enable any type of waveform to be able to travel through them. I talked about, so we have scalable geographic diversity because of the WAN, and also system resiliency. Okay, yeah. All right, we'll move on to the next slide. I think I got everything I wanted to cover for that. Let's talk about how things are being used currently in this similar type of architecture. So right now, where we see this approach being used is in these applications called ground stations as a service. And so what happened is in about 2014, there were a number of different LEO operators who primarily, well, most of them did Earth observation missions, and a lot of these startups didn't want to have to go out and build out their own ground infrastructure. So what happened is that they are actually contracting with folks like Microsoft and Amazon to buy this service called ground stations as a service. And what they do in this service is they tell Amazon or Microsoft, hey, my satellite's going to pass over at this time over these particular gateways, and I want you to collect on this band. So with edge devices that are out there currently, what happens is these edge devices are essentially just spectrum vacuums or signal vacuums. They take all this RF data, collect it, right, and they transport it using their own proprietary digital AF signals, which is based on this protocol. That's based on this not necessarily protocol, but like a data representation language called Avita 49.2, which basically just tells us how to interpret these digital samples. And those signals are transported over a network, and then they go to a cloud system where they're stored, and then later processed to be able to extract out what the actual download, if you will, of those satellites were at that time. And then the those Earth observation products can go directly from their digitized waveform representative of those signals down to their specific data products and release. So there's a lot of advantages for these LEO markets to do this. The other popular business model or application that this is that's been that this has been deployed is with within TT&C telemetry tracking and control of satellites. So we have and we have cases where we have these low bandwidth, not necessarily latency dependent or latency constrained applications where these edge devices can be able to collect this information and support these new services to give these operators ground up advantages. So this is how we're seeing some of the ecosystem transfer. So what in terms of SATCOM, what can we expect moving towards the future? So the Army recently put out, not well, it's recently, I guess it was last year, their first look at what's called the Enterprise Digital AF Multi-Carrier Modem. And in that, they had a notional architecture in terms of what they thought, what their vision was for digitized architecture. And I'm just showing you kind of my interpretation of it with my own diagrams and figures and whatnot. So very, very similar to what I showed earlier. And we have the digital modem bank there, the digital IF LAN, and there's this new network element that's similar to combiners and dividers from the analog system called the digital IF aggregator deaggregator, or affectionately called the DAD. And essentially, what that does is it takes these digital IF individual IP streams and combines them into a signal stream to send them to an L-band edge device. And those DADs could be rerouted out to another, let's say if there's some type of remote site that needs to get these signals, they can be used as like a point of collection and routing out to those sites. Although we could see, as I showed in my previous figure, we could see that those edge devices could be those devices that provide that combining and splitting functions. But there's definitely something that will be different in ground segments in the future. Right. So I talked a lot about saying if there's an appropriate digital IF protocol, interoperable digital IF protocol, and I get really really excited about this particular topic. In that, just in August there was a consortium that was pulled together called the Digital IF Interoperability Consortium, or as we affectionately call it, DIFI. And this is an IEEE standards body that's been formed by industry and the government. Last I checked, there's pretty close to 30 different members that are in this from industry and the government, ranging the whole gamut from satellite network operators to vendors to L-band switching system vendors to, like I said, this, like I said, there's many different space forces and there's many different people that are joining this group. So this is very, very exciting in that we're starting to see a lot of push for creating this interoperable protocol. And what Diffie is, what was released initially in the first Diffie standard was just essentially a couple data packets, signal data packets, which one signal data packet and two context packets, which allow you to just be able to interpret what those packets of digitized samples are. And those are going to be going over UDP, over IP, and Ethernet. However, this is okay for if you have like a direct connect, probably even a LAN connect where you have very low amount of traffic. This is probably okay. However, there is still the need for some additional functionality that's going to go to this digital IF protocol. And these things are flow control, packet loss recovery, and security. So these are things that are being pursued right now in the Diffie consortium to be able to enable this to become a reality. But like I said, the first iteration is out there right now. just want to touch on what those different components are that the Diffie consortium will be working on. So flow control, basically, this just is the ability for us to deliver digital samples to match the rate of the consumer. So you might not know this, but actually, there's a difference in clocking between, there will be a difference in clocking between the digital IF modem and the edge device. So it's important that we have the rates finely tuned in so that data can be processed as fast as it's processed at the same rate it's received. If too much data is sent to the edge device, what can happen is a buffer overflow, and what that'll means is that we're dropping digital sample packets. And this will kind of be, this is sort of similar, this flow control problem is kind of sort of similar as a real-time streaming video. It's where, like, let's say if you're not sending fast enough, what will happen is you'll have instances where the video will stall or will stall and stop because it's waiting for packets to come. They're either delayed or drop. That's a different problem, but anyways, or if they're coming too fast, you might have skips in the video. So those are things we want to avoid, especially in SATCOM. Those problems can cause modems to become a lock and are pretty severe. Packet loss recovery is just another technique to be able to deal with transmissions of packets over a wide area network. Specifically, like when we're doing normal transmissions, the traditional protocol that's used is called TCP. And what that uses is just standard retransmissions and the far side saying I didn't receive a specific packet. Well, particularly with real-time streaming digital samples, retransmissions may not be good enough, and also they introduce a buffer delay, which is something we want to try to minimize. So there's techniques like packet forward error correction that need to be explored for that. And additionally, and the final thing is that security. So we have these digital IF streams going everywhere now. There's going to be the need for authentication for edge devices to authenticate their receivers, and for digital IF modems to authenticate the edge devices to say, hey, I can send you, you can send to me, to make sure that there's no hijacking or interception redirection of streams, and then possibly even things like security for those individual streams. All right, so I talked about digitization. I want to see if there's any other questions. I think there's one in the attendee chat. Bill, did you have any questions for the digitization section?
Yes, we did have a couple more questions come in. I believe that you answered the two previously, but I'll read those over just for completeness. So our initial question, our first one was from Stephen Johnson. He said, "What is the maximum distance between the digital IF modem and the edge device?"
Mm-hmm.
Yes, I believe that
Right.
was
Yes. Yeah. We answered that. And for the LAN case, local LAN is probably going to be between 2 to 40 kilometers, and then obviously with the WAN case, it's unlimited. It's limited to how much delay you're willing to accept.
Okay, thanks. Our next question was from James Sawal. He said, "Who builds or owns the edge device, and how do we ensure that it is not proprietary?"
Right. So there's very limited amount of edge devices out on the market today, and most of them are for those applications that I mentioned for the ground stations as a service. So look out, edge devices are coming really soon. So, and digital IF modems are coming really soon.
Thank you. And our newest question is from Stephen Johnson as well. If digital IF is used for GW resilience back up to sites over 40 km, how do you deal with timing issues over long distances when the network switches gateways?
Yeah, that's a good question. That has to do with some of the flow control issues. That's the primary issue is flow control. And that is an issue we're working through the Diffie consortium right now, of which Envistacom is a member of the board and also the working group, specification working group. And that'll probably be something similar to, and we haven't worked all the details out, and this is just my own personal feelings, is that this is probably something similar to PTP, precision time protocol at the IP layer. And that'll allow just synchronization in terms of that way, just exchange of clock information. And then that might be good enough to correct most of the things in terms of the packet interface. Local clocks will always need to be used as well. There's also some issues that we need to explore in terms of that. But yeah, that's a really great question, and that is an issue that we're going to work through in the Diffie consortium.
Thank you. That's all the questions we have at this point.
All right. All right, let's move on to virtualization section here. So looking at virtualization, so what the outcome is, I talked about this at quite length, how the digital AF protocol, that's kind of like the linchpin for digitization to be able to work along with these different edge devices and digital AF modems. But what that will enable is just the move to common hardware platforms, which is going to further enable that springboard for virtualization to take off. And in this virtualization section, there's kind of three main topics I want to talk about. It's just NFV, or network function virtualization, operational support systems and business support systems, and management network orchestration. And we'll talk in a lot of detail about what these individual are. But before I continue, I just want to talk about first, when I talk about virtualization, especially in the SOAR report, even in this paper, I mentioned kind of two different perspectives to look at it from. The first perspective is just virtualization from an abstract concept, and this is just that first abstract concept. And essentially, the nuts and bolts of it is that, in a normal system on the left, we see is that we have some type of common hardware. We deploy our operating system on it, whether it be CentOS or other type of a Linux platform, Windows or whatever, and we put our applications on top of that. And that's how most of us work with our laptops and other computers. However, with in a virtualized system, we add another layer into this cake, and that's called hypervisor. And what that allows us to do is do that resource abstraction, so that we can do individual virtual boxes or virtual computing environments on top of that. And that's kind of like fundamentally what virtualization is. It's the ability for us to take and abstract out our resources into reconfigurable units such that we can assign them to different functional components. Now, virtualization, when we talk about in the larger sense, is if I go back to my diagram here, is I'm talking about virtualization in terms of like that concept, and also these other three things: NFV, OSS, and MANO as well. So that would be the second perspective. So I'm going to talk about, when I talk about virtualization now, it's going to kind of be within that second perspective. So before I actually talk to this figure, I need to give this a little bit of background. And essentially, what happened with the mobile network operators like Verizon and AT&T is that when they migrated their radio access networks from 2G to 3G, 3G to 4G, what happened was is that with each evolution of the architecture, there were sets of boxes that were basically, they were proprietary built, right? They had conjoined hardware software firmware in them to be able to perform these different network functions. So every time they had to do a refresh or upgrade to the next generation systems, they had to pretty much replace all this equipment. So that was something that they didn't really like to do, because for one, it affected their businesses, and also it was very costly. So that moved them to want to be able to use virtualization in the first perspective, to be able to achieve a higher objective, in that if we were to virtualize these individual network elements and put them together to form type of useful function, what would that look like? And that's where network function virtualization was born. So this is just a very generalized and simplified version of what the network function virtualization architecture looks like. So at the very, very bottom of the network function virtualization layer, we have our infrastructure layer, or NFV infrastructure. And what that is, that's just all the computing resources that are provided for. And of course, we talked about how the hypervisor provides virtualization to those. The virtual network function layer is the layer that is just basically our individual virtual machines or whatnot. They're connected together. And above that, we have our OSS, BSS systems. These are basically the business components and representative functions that allow a network operator to execute and run these virtualized systems. They could even be application portals for customers to be able to order services. And then the MANO system, or management network and orchestration. What this is used for is basically has the responsibility for deploying, configuring, and termination of different virtual network functions. So to put this in kind of a more of a higher level context, if you purchase services or computing resources on Amazon, what that looks like is you enter kind of like your application portal, and that'll allow you kind of selection of different, like a menu of different types of computers you want based on RAM, hard disk, and possibly CPU resources. So that would be like your application portal. And once you like click on that button, what essentially happens is that their manual system will go off and create a virtual machine based on whatever hardware resources they have available that gives you that back. So that's at a very high level how it works. For the virtualized ground segment, if we take these concepts and we put our virtualized ground set or our digitized ground segment underneath that in the infrastructure layer, you can kind of start to see and realize how these things might operate in the future. The first, with the digital modem bank, because we're basing these on common hardware, we can have virtual network functions and SATCOM functions working on here. This includes waveforms, perhaps things like SD-WAN, or even applications that we may have not thought of yet. They don't necessarily have to be waveforms. They could be anything that can receive and receive signals and transmit signals, or applications we can deploy in these different types of systems. If I was to say this is pretty much going to be like what I want to say, like the holy grail in terms of what SD software-defined radio wanted to be. The edge devices, probably not. They may just end up being like a physical network element instead of a physical network function instead of maybe a virtualized network function. But there's also the possibility of deploying digital AF transport hosts to be able to help manage traffic and whatnot going through. And then also, there's not going to be the need for a specific box for you to deploy your network management systems in anymore. This could just be deployed on any system, which I think the industry has already moved to today. That network management system will be then virtually connected all together using these concepts of virtual network functions. And we see some of these concepts are being heavily leveraged, especially for SD-WAN type architectures. If you look at it, there was a recent announcement that SES actually went out and is collaborating with another company to deploy and virtualize all their different SD-WAN functions so they can enable more effective data transport across their networks. So I'd like to just go through and just have like a little bit more specific example. I talked about the Amazon example, but I just want to go through and show you how these signals might go through different layers to perform this thing called a service chain. So a user operator might, let's say, might want to have a specific waveform, specific functions, they have some type of order in mind, a service level agreement, whatnot, that they want to try to be able to invoke and realize on their own system. So the service order will be processed by the OSS/BSS system. And then it translates that into some type of service chain request. So when that service chain request is sent to the Mano system, what it'll do is it virtually figure out and configure all the individual virtual network functions that need to be deployed, as well as allocate those resources from the infrastructure onto the systems. Then once those things are completed, service confirmation is given back up to the OSS/BSS system, and then any monitoring and control can happen through the user operator functions interfaces. So essentially, we're getting close to having the technologies all in place for us to deploy built-to-order SATCOM networks. And to me, this is very, very exciting, and this is something I would probably told you. If somebody told me this maybe 10 years ago, I probably told them they were crazy. But just the fact that we see these technologies already being deployed and used in other different telecom segments, and to know that we can do them today very, very soon is actually really, really encouraging and really, really exciting as well. So this gets me very, very, very excited for what the future is going to bring. Okay, now I just have some basic use cases just to illustrate some of the concepts that I've taught. Oh, I think we had a question. Do we have another question about virtualization, Bill?
No, I didn't see one come in.
Okay, all right. Well, let's keep going then.
All right.
So I'm just going to close out. Just have a couple of use cases to demonstrate or give you a couple of illustrations about how these systems might operate in the future. So I'm just going to show, like I said, just two of them. The first one's just modem and terminal agility. And just give me a minute. Basically, what this is just showing is that we have our virtualized architecture here based on the NFV architecture, and we've got our Mantle system, which has these different potential virtual. We've got waveforms we can deploy. These are VNFs that could be deployed. We've got a monitoring, like this could be like a spectrum monitoring type application as well. We also have like a artificial intelligence classifier, like we might be looking at signals trying to find something in the signal, whether it be like another interferer or something like that. So basically, we have kind of like this kind of menu of things we want to deploy. And our current VNF we're showing here, we've got stuff assigned in the red. So these are our red virtual network functions, which are deployed on the red infrastructure here. And then we've got our blue infrastructure, our blue virtual network, our virtual network functions, and then our blue hardware elements that are deployed with those functions. So what I want to illustrate with this is that our digital modem bank, it's capable in the future, will be capable of deploying these functions however it sees fit. It doesn't necessarily matter which waveform or which applications I use, but I can use them however I please and see fit. And assuming that we have multiple beam, multiple access to all these different SATCOM networks as well. That's probably in a SOAR report in and of itself, but let's moving on. Let's go to the next slide. And I talked a little bit with resiliency, system resiliency, and the earlier slides when I discussed digital app. But this is just to illustrate the point. Is that we have just different paths here. The red path is just showing, we have this digital modem bank, this digital modem bank going across this digital app LAN, going across this edge device and the RF transmission system back out to the terminal out in the field. But I've also showed these two paths, the blue path and the purple path. What they show is that the originating gateway and the what I call the digital transmission system, and which includes the edge device and the RF transmission system, don't necessarily need to be at the same location anymore. If there is a digital IF WAN that where these or I call digital IF interfacility link that goes through here, we can enable. Let's say the red path experiences some type of interference. Well, that path can then be rerouted out through, let's say, through SAT3 instead of through SAT1. So this is just other ways that resiliency can be realized through using alternative SATCOM. Through using different edge device paths or originating from different digital modem paths. And that's kind of the big thing in terms of what digital life brings to the table. The other thing too is I didn't really talk about this, but you can imagine now also is that from a SATCOM terminal perspective, we can start to increase the distance between our antenna and also where our signals go back to. Some people refer this to as like a baseband, or if you're in like an operations setting, it might be like a tactical operations center. So your antennas or SATCOM connections can be now dragged very, very far out because we're not restricted by an analog cable. We can use a fiber and send that way out. So that's another aspect of how the digital AF and virtualization can help in terms of operational deployments. So that's all I had. I think there was one more question, or maybe two more questions, Phil.
Yes, thank you for the presentation. We did have a lot of feedback. Very interesting topic. I would also like to remind our members that the state of the art report will be published to our website shortly. So keep an eye out for that. The recording of this webinar will also be on our YouTube site shortly as well. So when you do get a chance to read the state of the art report, if you do want to refer back to the presentation, kind of help put some of those pieces together, that will be available. But we did have one new question come in as well. I believe we addressed all of the others. So these are some of our first questions. So as I cycle through, we addressed this one as well.
Oh, can you go back to another one? Can you go back
Sure,
one?
sure, no problem. Hold on one second. I can renew all of them. Go from there. So this was our first question. What is the maximum distance between a digital IF modem and an edge device? I believe that was answered. Then our next question was who builds or owns the edge device and how do we ensure that it's not proprietary? I believe that was answered as well.
Yep.
Then we had a question about dealing with timing issues
Right.
in relation to the distances. That was answered. So the next question we have is, can you say a few words about basic SATCOM resiliency?
Yeah, that's I mean, we talked about how some of that could be used with digitized, with the digital IF interface. We can improve resiliency that way. Um, Resiliency is kind of like a hard problem because it's like one of those things where you have like all the blind men touching the elephant, and they all touch a different part. The other thing that's also exciting about SOCOM resiliency is that you can now start having independent uh, I guess SATCOM systems simultaneously, and then able to coalesce those individual outputs from those waveforms into a single data point, and maybe using it to spread across. That could be another way you could increase socket resiliency. The other thing you could also do is, like, let's say that you are in an operation of some kind, and you have a narrowband waveform, but for some reason your mission requires you to go to some type of protected or wideband type waveform. Well, that could be something that could be deployed as well. So those are just three different ways these new concepts can improve SATCOM resiliency.
All right, thank you. And we have one more question come in from Jacob. How close is
Oh, yeah.
Diffie in addressing flow control?
Yeah, that's a great question. It's just something that we just begun to address. It will be interesting to try to see how it all plays out, just because of uh, there's always competing interests and whatnot, and also the move toward argument towards, we want to make sure that hardware vendors have a way to differentiate themselves, but also be interoperable. So there's always that kind of that uh, what's the word, conflict of interest at play. So, but I think that flow control, I feel pretty confident that flow control will be something that will resolve before the end of the year. I'm pretty optimistic that it'll be done. It's like in terms of, my feedback to the Diffie committee right now is that, yeah, this is the next thing we need to address, because this is probably the most important thing right now, in my opinion.
Okay. And I believe that is all of our questions that we have for today. It's actually 102, 2 minutes over, so perfect timing. I would like to thank Dr. Deaton for the presentation today. Again, these slides are up on the website. The recording will be up in a couple days. Our next webinar will be March 22nd on data science and machine learning enabled terminal effects optimization. We hope to see everybody there as well. And thank you for today.
Yeah. Yeah, thank you everybody for attending, and thanks for the questions. I really appreciate it. And feel free to get a hold of me on LinkedIn, or you have my email address right there if you have any other questions or whatnot. So thank you again.
All right. Take care.